Alright, what's going on? Today we're doing another LeetCode problem. This one's called maximum depth of binary tree. So we're basically given the root of a binary tree. They want us to return its maximum depth. So the maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So it's basically just counting how many levels there are. The first node counts as level 1, then the second level is level 2, and so forth. So this binary tree would have a return value of 3 for the maximum depth. So pretty straightforward problem statement. There's a couple ways you can do this. I'm going to show both the I'm going to do 2 depth first search solutions, recursive and iterative. So let's go over the basically recursive solution first. So I'll just draw a tree here. All right, and I won't make too big of a tree. So for our recursive solution, basically what we want to do is we want to just keep calling the function. We want to keep calling a function recursively on each of the children nodes, basically returning 0 once we reach a null pointer, and then adding 1 basically every time we call the function. So what that would look like, and being that we're searching for null pointer, it's important to be aware of where those null pointers are. So I'm actually going to visually illustrate that. So basically at all those leaf nodes we have null pointers. So we would start with calling the function up here, and the code would have to call the left children first and then the right children. So basically what's going to happen is you would call the function recursively on the left child here. That would happen again, so you would go down to the left child, and that would happen again until you reach a null pointer here. And basically at this point we would return 0, and then we'd start backtracking. We basically, the recursive call stack would start retracing its steps. So we would go back this way, and we added a 1 every time we called the function. So there would technically be a 1 here, noting that this is like the first level, and this kind of goes backwards, right? So in a sense, so 0 here, 1 here. At this point, since we've reached this node, remember we're calling the function on both of the children. So the function would actually get called this way on the right child. It would reach that null pointer, so we'd return 0. We'd come back up here, and we'd have a 1. And the way this works is, in addition to calling max depth on both children, we're going to take the max of those max depth. So the max of 1 and 1 is obviously just 1. So we would backtrack again up to this 2, adding 1 again, so we would get a 2. Then we would call that function recursively on the right child. So let me get the right color there. So we'd go down this way. But remember, it's left to right still, so it would try to go this way first. It would go left. There's 0 there. It would pop back up, and we added a 1, so we get a 1 here. And then it would be called on the right child. We return a 0 there at the null pointer. We pop back up, and we have a 1 here, so the max of 1 and 1 again is 1. So adding 1 to that, we get 2. The max of 2 and 2 is also going to be 2. And I forgot to draw the arrow for us popping back up here. And then we'd pop back up to this root node, and we'd have a 3 because we added 1. So we have a 3 there. So basically the max depth of all of, starting from the left child here and doing all those recursive calls would be 3. Finally, we can go down the right side here for our depth first search. So we'd go down the right side. There's not a null pointer here, so we're gonna try to go left, and we see a null pointer, so it's 0. We pop back up, we add 1. At this point, we would go right. We see that null pointer, it's a 0. Pop back up, and we added 1. So the max of 1 and 1 is obviously just 1. So popping back up and then adding a 1 to that 1, we get 2. And then obviously the max of 3 and 2 is just 3. So we would return the max depth of 3, and that's pretty much our answer for the recursive depth first search. In terms of time and space complexity, our recursive call stack is going to have at most a space complexity of, so the space complexity is going to be big O of h, because we're never going to have more than the max depth of nodes, also known as the height of the tree h. There's never going to be more than that many recursive calls in our call stack. So that's the space complexity. And then the time complexity is just going to be big O of n, where n is the total number of nodes in the tree, because we have to visit every single node to ensure we find the correct max depth. So let's just go ahead and implement this in code. So the code for this is extremely simple. So basically, once we've reached a null root node, so if not root, we can just return 0, and then we start popping back up. And then otherwise, we're going to return the maximum of that function called recursively, so max depth of the roots. So whatever node we're currently at, left child, and we need to call that on the right child of the root node. And the whole time we're adding 1 at each node, or at each level pretty much. So as we're popping back up from 0. So that's pretty much it for the code for the recursive solution. It's a pretty much the most elegant code you can write for this problem, and it's have a little bit of a bug there. But yeah, pretty much the cleanest code you can write for this problem. So let's go ahead and look at the iterative solution as well, just for fun. So the iterative solution is going to have, right off the bat, it's going to have the same time and space complexity. So the space is going to be big O of h, because if you step through the code for the iterative solution, you'll never have more than h, where h is the height of the tree. You'll never have more than h nodes in the stack. It doesn't necessarily reflect the path, the deepest path of nodes, but you'll never exceed h nodes in the stack, and you can test that, and I'll show it right now. So, but the time complexity is also going to be linear, like the recursive solution, because we have to visit every node to make sure we're getting that true max depth. So that's the time and space. Let's just whip up a tree here. So probably just do the same tree that we did for the recursive solution. So, or who knows, I forgot at this point, but let's try it on this tree. So we're gonna have a stack, and basically the stack is gonna contain node, as well as it's going to be like a pair. So it's going to be the node and then whatever the height is at that node. So at first, when we push the root node to the stack, we know that height is going to be 1, and I'll just label these levels, even though we don't really know what they are as we're iterating through the code, but we can see it visually here. So we know for sure that the root node is on level 1, so we push that as a pair to our stack. So we have that first node, and then we have the height 1, or depth 1 at first. So with each iteration, we're basically just popping from the stack and then pushing its children in the same manner. So we would push this 2, and then we push whatever, for the depth, we just add 1 to whatever the current depth is. And the current depth we extracted basically from the last pair we popped. So that was 1. So now we know the depth is 2. We'll do the same thing when we push the 3 node. So we have current depth of 2. So now we're going to pop from the top of the stack, push its children. If they're non-null, so you notice how both of the children for this 3 are null, we're not going to push anything in that case. So then we move to the next element that's at the top of the stack, which is this 2, and with depth 2, we're going to pop it and push its children. So its children are going to be at 4. We add 1 to the current depth, which was 2, so now it's 3. And we're also pushing that 5 with the same depth of 3. So now we can go to the top pair there at the stack, pop that. And by the way, you know, we're this whole time we're keeping track of a max, which is a max depth, which we just use a max function on and look at whatever the depth is of the current node we're on. So we just pop that 5 because it doesn't have any children to push. Same with the 4. And after that, you know, our max depth would have been 3, so we return 3. So let's get into the code for this. It's a little bit more code for the iterative solution. So we're still going to check if the root is null. We can just return 0 in that case. We're going to have a stack of pairs, and we're going to use a tree node pointer and an integer for the depth. And I'll just call the stack st. We're going to push the root node first, and we know that has a depth of 1. We also need a max depth variable, and that'll just be 1 at first also, because we know the root node is non-null. So we can loop while our stack is non-empty, so while the stack still has pairs in it. And we can take that, whatever node we're at currently, by accessing the top element of the stack, and that's going to be the first pair member, and then the depth that we're currently at. And let me declare that out here so we don't have to keep redeclaring. So depth, that'll be like the current depth we're at. That'll get set to the top pair of the stack, but the second pair member. Okay, and then we can basically calculate that current max depth by saying the max depth is going to be the max between whatever the current max depth, or the previous, you know, whatever the overall max depth is, and then the current depth we're at the node we're looking at. So then we can just push the children to the stack. So, and it's a stack of pairs, so well, first we need to pop that from the stack, right? So stack pop. Okay, but now that we've popped that from the stack, now we can push the children. So we're going to say stack.push. It's going to be basically to construct that pair. We'll take, well, we have to have an if statement, right? Because we're only pushing non-null children. So technically, yes, first we need to say, you know, if the left child exists, then we can push, the pair of consisting of that left child node and then the current depth plus 1. So that's how we're going to do that. And then same exact thing for the right child. Okay, and then at the end of this, we're going to just return the max depth. So that's pretty much it for the iterative solution. Again, both the time and space complexity should be the same for these. I personally prefer the iterative solution because I like how we don't have to rely on the operating system for recursive call memory limitations and the call stack. I couldn't think of the word there, but anyways, yeah, hopefully this video helped you understand the problem better. If it did, leave a like and subscribe, and I'll see you guys in the next piece.